Over the past few years, AI algorithms have achieved feats like rapidly assembling millions of protein structures and mapping climate dynamics with incredible precision. But for researchers trying to integrate these tools into their own labs, the reality is far less glamorous. They hit a wall of fragmented literature, constantly shifting software architectures, and a barrage of technical buzzwords. This leads to a common misstep we call the implementation trap. It happens when the very first question a lab asks is, which specific AI model should we use? Answering that question immediately is almost impossible because the algorithms themselves are transient. The technical landscape evolves so quickly that an ad hoc choice today is often outdated tomorrow. Escaping this cycle requires a shift in perspective. Instead of hunting for an algorithm, researchers need to focus exclusively on identifying the exact scientific bottleneck they are trying to overcome. We need a map that translates those scientific bottlenecks directly into AI capabilities. That map is the AI for Science Strategic Compass, or AFSC. This is the AFSC strategy matrix. It shows a comprehensive, domain-agnostic architecture of possibilities by plotting laboratory challenges against technological functions. Looking closely at the top row, the x-axis categorizes what science actually needs into 4 universal bottlenecks, or tensions. These are complexity, constraints, scarcity, and the combinatorial explosion of search spaces. Panning over to the leftmost column, the y-axis organizes what AI can do. It breaks the field down into 6 core functions, like the ability to represent data, reason and infer, or simulate systems. The intersections of these rows and columns create a stable vocabulary for problem-solving, remaining independent of specific software, hardware limits, or trendy model names. By plotting your specific laboratory tension against these broad AI functions, the integration process becomes a rigorous strategic choice rather than a guessing game. Let's trace a specific scientific bottleneck to see how this works in practice. This isolated column represents the explosion tension, which occurs when a parameter or design space grows exponentially. A researcher facing this problem can approach it from entirely different angles. They could use the represent function to physically compress the data space, or apply the reason function to prune away impossible branches early on. Continuing down the same column, they might instead choose the simulate function to accelerate evaluation times, or rely on generate to seed entirely new candidate solutions. We can also read the matrix horizontally, isolating the represent function to see how a single AI capability adapts its purpose. When dealing with raw complexity, representing data serves to factorize it into manageable pieces. But if the problem involves experimental constraints, that exact same function is used to robustify the data against noise. Moving further right, representation amplifies weak signals in the face of data scarcity, or acts to compress information against combinatorial explosion. There is no single correct algorithm. Labs can choose from multiple strategic routes, tailoring the AI approach to their exact problem. To put this into practice, the AFSC uses a straightforward 5-step process to map a raw scientific problem to a concrete tool. In steps 1 and 2, researchers identify their dominant tension. They scan that specific column, looking for cells marked with stars, which indicate high-leverage AI entry points. For step 3, they open their chosen cell. Inside, they find distinct strategic pathways. These are the specific mechanism-level options available at that intersection. In step 4, the team evaluates those pathways against their own local reality. They filter the options based on their available computing power, data volume, and in-house expertise. Finally, in step 5, the strategy is fully validated. Only now does the researcher instantiate it by selecting a specific method family and model architecture. If a selected pilot model fails in the lab, the research team doesn't have to start the entire process over from scratch. They simply return to the strategy layer and choose a different pathway within the exact same cell. By focusing on foundational mechanisms rather than transient model names, researchers bridge the gap between domain science and AI engineering. It ensures their strategy stands up to both rigorous peer review and the test of time.